Hello, so hi there everyone. We're now on our next video in number theory, and we're going to continue our discussion in the classical milestones in number theory. Now we're going to touch Euler's theorem, but not necessarily in this video. We're going to start with some foundations with the Euler's theorem. Specifically, we will be talking about Euler's phi function, the Euler's phi function. That is, of course, directly connected to the Euler's theorem. So let's talk about that. We know Euler as the king of mathematicians, or popularly known as the king of mathematicians. He's the one who answered the bridges of Königsberg problem in Prussia, about the number of bridges that you can um what do you call that, cross without going back. Actually, that's an Euler circuit, and that is the origins of graph theory and, of course, the basics or the basis of topology we know as topology right now. So that graph theory is the geometry of location, okay, the mathematics of location without even looking into the lengths and the widths and the weights of everything. So it's all about locations. So anyways, that's a brief history of Euler. So let's talk about first definition 4.13 before we go to the Euler's theorem. So this is Euler's phi function, which we will use definitely in the Euler's theorem. So this is the phi, right? The Greek letter phi. Okay. So we let m to be a positive integer. Then Euler's phi function, denoted by phi of m, in which this m is any positive integer, denotes the number of positive integers which is less than or equal to m and relatively prime to m. Okay, so again, this Euler function gives us the number of positive integers less than m or equal to m, which are also relatively prime to m. Relatively prime to m. Okay, now um, let's go to some examples of the Euler's phi function so that we can understand it more. Let's have this is example 4.14. It follows by definition 4.13 that, let's start with the first number. Euler's phi function, phi of 4 is what number? So we're going to think of, so since our m is equal to 4, so we're going to think of numbers. Okay, I'm gonna change my color to red. I hope it's okay. Okay, I think this is okay. Now, the number of integers, positive integers, which is less than or equal to 4, and which are relatively prime to 4. That is, they don't have common multiples or common factors. That is, their GCD, if we're going to pair them, is 1. So what numbers are there? Are that? Okay, what numbers are that? So we know first that there's only 4 integers below 4 or equal to 4. So we have 1, 2, 3, and 4. So we can see that 1 is relatively prime to 4. 2 is not because they have a common factor, which is 2. 3 is yes, and 4 is not because they have a common factor, which is, well, it themselves, 4. So therefore, the phi function of 4, phi of 4 is equal to 2. Why is that? Since there are two positive integers which are less than or equal to 4 and is relatively prime to 4. Namely, we have 1 and 3. 1 and 3. Okay, if you want to write that in a sentence, so therefore, this is because since 2, since there are two positive integers less than or equal to 4 and are relatively prime to 4. Okay, that is, namely, we have 1 and 3. Okay, so 1 and 3, or we can simply look at that. So in our next example, let's answer this directly. Okay, so we have the what's the phi of 9? So what numbers do we have which are relatively prime to 9 and it is less than or equal to 9? So let's list it. 1. 1 is a yes because it's relatively prime. 2 is a yes. 3 is not because 3 is um they have a common multiple, which is 3. 4 is a yes. 5 is a yes. 6 is not because they have a common factor, which is 3. 7 is a yes. 8 is a yes. 9 is a yes, is a no rather, because it's common factor of itself. So we have 1, 2, 3, 4, 5, and 6. So therefore the phi function is 6. So I think that's clear enough. For the 12, let's count them. Um, 1 is a yes. 2 is not because they have a common factor, which is 2. 3 is not a common factor, which is 3. 4 is not a common factor, which is 2 and 4. 5 is a yes. 6 is not a common factor, both of 2 and 3. 7 is yes. 8 is not because the common factor of 2. 9 is not common factor of 3. 10 is not common factor of 2. 11 is a yes. You know what? 11 is a yes and 12 is not. So how many? So 1, 1, 2, 3, 4. So the phi of 12 is 4. Okay, that's how you answer the phi functions of integers. Just one remark from this: the phi function of 1 is equal to 1. That since just a remark, this is because since 1 is less than or equal to 1, and okay, since 1 is less than or equal to 1 and it is relatively prime to 1. Why is it relatively prime to 1? The GCD of 1 and 1 is 1. So it's relatively prime, okay, even though it because that's you can see here from this example that 1 is a special number. Okay, it's relatively prime to 1. The GCD of 1 and 1 is 1. That 1 is less than or equal to 1. So therefore the phi of 1 is 1. So let's have more examples of this. I have here one more example above. Okay, here you go. So it's your time to shine, and let's try to answer. You try to answer this, and then we'll answer this all together after you. Okay. So like, you can pause the video right now. Okay. So let's try to answer. What's the phi of 11? So how many numbers are there relative to 11 and it's less than 11? So notice that 11 is a prime number. So if it is a prime number, it doesn't have any other factors than 1 and itself, right? It doesn't have any factors except 1 in itself. But the GCD of 1 and 11 is 1. Okay, so therefore we should include 1 uh, to our answers. And what is our answer here then? Our answer here is, well, it includes 1, 2, 1, 2, 3, 4, 5, up until actually 10. 11 cannot be, okay, because they have a common factor. So therefore the answer is 10. Okay, 11 cannot be. How about 18? So there are integers which are relatively factor to 18. So let's just try to think of that. 1 is one of them. Oops, sorry. 1 is one of them. 2 is not common of 2. 3 is not common of 3. 4 is not common of 2. 5 is a yes. 6 is not common of 3 and 2. 7 is a yes. 7 is prime. 8 is not divisible by both divisible by 2. 9 is not both divisible by 9 and 3. 10 is not both divisible by 2. 11 is a yes, since 11 is a prime. 12 is not both divisible by 2. 13 is a yes. 14 is not both divisible by 2. 15 is not both divisible by 3. 16 is not both divisible by 2. 17 is a yes. And I think that's it. So the phi of 18 is 6. Oops, sorry, let me clear that up. 6. Okay, so these are our answers for your example 4.15. Hopefully you got the same answer there, which is 10 and 6. Before we end this video, I'll just give you some lemma, just a generalization or a remark from our example 1 in 4.15, lemma 4.16. It states here that, okay, from our lemma 4.16, a positive integer p, okay, a positive integer p is a prime if and only if the phi function of p, the phi of p is equal to p minus 1. Okay, so that's a lemma. So I think you can imagine that the phi of 5 is equal to 4 by this lemma. the phi of 11 is equal to 10, the phi of 7 is equal to 6. Likewise, the phi of what are the other prime numbers? The phi of 17 is 16, okay? And it continues on and on. So to get the phi number, the phi function, Euler's phi function of a prime number p, so just deduct 1 from that, and that's your answer for the phi function. Okay, so after this, we're ready to define and deal with Euler's theorem. That will be in the next video. So hopefully you will understand Euler's theorem by now because we have defined Euler's phi function here. So that's it for this video. Thank you very much for watching, and I hope that you would like and also subscribe. Okay, thank you.